Hello everyone, let's welcome our next speaker in Security Dev Room on FOSDEM. It's Lukáš Vrabec and his talk about SELinux with container runtimes. Let's welcome Lukáš.
So can you hear me fine? Okay, before we start with the presentation, I have one question for you. How many of you know SELinux? So many people. Okay, that's great. So let's start with the introduction. My name is Lukáš Vrabec. I'm a SELinux evangelist at Red Hat. Some people already call me that. I'm member of security technologies team at Red Hat, and I'm RHEL and Fedora contributor to following packages, which is SELinux policy, Xguest, Udica, and netlabel tools. Here is my blog post. If you are interested in some CVEs and how SELinux mitigate them, you can find some interesting blog posts and GitHub link and also Twitter. So why we are here? I'll use a nice example of one of my colleagues from last week. And in one OpenShift cluster, the SELinux is enforced by default. On this cluster, there are almost 200 pods running more than 600 containers, and 134 containers run as privilege. In this case, I mean there is no SELinux isolation for them, and 134 is so many containers, right? So privileged containers are really scary, and today I would like to teach you how you can generate a SELinux policy for every container. So quick introduction to SELinux. I make you SELinux experts in less than 5 minutes, hopefully. So SELinux, you probably know it, is implementation of mandatory access control, but we can say it's a process isolation technology for mitigate to mitigate attacks via privilege escalation. One of the most important things you need to know are labels, right? In this case, there are two examples, container_t and container file_t. These labels are assigned to processes or to system resources. A system resource could be directory, file, symlink, socket, and many more. And these labels are assigned to processes and system resources by SELinux security policy. So how labels look like in reality? They are stored related to system resources. They are stored in extended attributes of the file system, for example, x2, x3, and x4. There are two ways how you can see the SELinux label of some specific file. In this case, it's /etc/password, and as you can see, the whole SELinux label is what is written in red. But in this case, we are interested only about the type, which is the third part of the label, which is password_file_t. So for processes, we can use a parameter capital Z for PS command, and if we want to grab some label of container, you can see that in the example there are 3 containers, and each container has a same SELinux type, which is container_t, which is here. SELinux security policy describes the interaction between the processes and system resources, right? And we are using for the interaction allow rules, and this is the example of the allow rule. The first is keyword allow, that's quite clear. The second thing saying that any process labeled as container_t can read, open, and get attribute of files labeled as container_file_t. And what is important to say also that everything is denied by default, so you need to have explicitly allow rule inside the SELinux policy, which is loaded to kernel to allow some syscall. And basically that's it. You are now SELinux experts, and that's all you need to know for generating SELinux policies for containers, of course. Okay, so now we will talk about the generic SELinux policy. For each container, without some custom SELinux policy, we use the default one, which is container_t. This policy protects the host system from the container processes, and processes or containers with this SELinux policy can only read or execute files in /user, and these container processes can only read to only write to container files. As I show you, process type, that's quite simple. That's container with container_t SELinux label, and file is every file and directory on the host file system labeled as container_file_t. So this is really nice slide. I really like it. These are the list, just few of them, few of CVEs of container runtimes when there was a possibility that a process inside the container could escape from container to the host file system, and in several cases gets root access. SELinux blocked all of them. The latest one is from February 2019, when SELinux completely blocked this type of attack. Yep, I say that. Okay, so what about containers attacking each other? For this, we have also solution, and it's multi-category security, which is part of multi-level security. So this is the way how it works with MCS. We have two containers. Both of them has same SELinux label, which is container_t, but the categories are different. First one has category C1 and C2. Second one, category C2 and C3. In the middle, there are three files with same SELinux type, which is container_file_t. And as we can see, following container can access this file because C1 and C2 is subset of C1 and C2. What is interesting that a file in the middle doesn't have any category, and empty set is also subset of C1 and C2, and same situation for C2 and C3. So this is way how we are isolating containers between each other. This is the same slide, but arrows showing what is not allowed. So C1 and C2 is not subset of C2 and C3. So you can ask how you can label some directory as container_file_t. Container runtimes has a really nice feature. It's for sure supported in Podman, and I'm pretty sure that it's also in Docker. That if you starting some specific container, you can bimount, for example, in the example /var/lib/mariadb, and you put parameter capital Z. So container runtime engine will relabel on the host system this directory to container_file_t, also with the same categories like running container has. That's because of the capital Z here. If you want to have two containers and you want to share the same directory, you can put small z, which means the engine just relabel this directory as container_file_t with no specific categories. So, of course, this solution has several problems. The first one is that one generic default SELinux policy for containers is too strict for certain cases. For example, Fedora Silverblue project needs container to read and write user home directories. Second one, Project FluentD needs to able to read logs stored in /log/var on the host system. There is another case when default SELinux policy is too loose in certain cases. There is no SELinux network controls, which means that container can bind on any port, and there is no SELinux control for capabilities, which means that a running container has all Linux capabilities. So we are able also to solve this. So what's the current situation? What can you do with MCS and generic SELinux policy? Let's say we want to start a container with fluentd project and we want to bind out /var/log from the host system, and we use capital Z as a parameter. It's here, okay? And this is not good. Actually, it's pretty bad because all other confined services on the host system will not be able to write or read /var/log because the label will be container_file_t instead of var_log_t, which is the default label for this path. The worst situation, what you can do, you can use this ugly parameter, which is here, and basically you disable SELinux separation for that container. So this is the worst what you can do. So solutions. You can write completely new SELinux policy for your custom container, but this is the best solution, but it's really too difficult, right, for system administrator because you need to have, let's be honest, quite good SELinux expertise. The second thing what you can do is to add additional SELinux rule for the container_t type. This is totally ideal because you need to know how to write SELinux policy, and also these additional rules will apply for all containers on your system, not to just your custom container. So to solve all these issues, there is a Udica project. Actually, Udica means fishing route in Slovak. And Udica is a tool for generating SELinux security profiles or policies for containers. So the best way how to describe Udica, let's use following example. Let's start a container mounting /home with permissions read and write. Let's mount /var/spool with read-only permissions, and let's expose port 2021. So, as I told you, generic SELinux policy cannot read and write /home. Generic SELinux policy cannot read /var/spool for containers, but on the other hand can expose all ports. So I'm brave enough to show you live demo, but let's finish the slides and then I show you the demo. But what will be there is we start the container with the by mounts and ports as I described. Then we only run inspection of the latest started container, which is here. And Udica will generate SELinux policy based on the inspection of container with name my_container. Udica suggests or recommends to load following SELinux policies, which is this load command. We just restart the container with the following parameter, where we are basically saying to not to use generic SELinux policy container_t, but our, which is my_container.process, and that's it. Then just to prove it, when we run ps, we will see that our container is running with our new SELinux label. So how it looks like, what's under the hood. So the whole concept here is based on the block inheritance feature in SEL language, where Udica creates or combining rules from predefined SEL blocks, or we can say templates. So Udica inspects container and looking for mounts, ports, and capabilities, and combines these predefined blocks with the base one, which is base_container_.SEL. So this is the way we will use the base block, which is needed for reading and executing files in /user and reading configuration files in /etc. Then we will use a net block, which we need for binding on TCP port 21, which is labeled as FTP_port. And next block is home, which we need for reading and writing to user home directories. Udica basically inherits allow rules inside these blocks and generate new SELinux policy with the name my container. We also mount /var/spool, right, inside the container, but for this there is no predefined block. So what Udica can do is to look to directory /var/spool, find all possible SELinux labels which could be inside this directory, generate block, in this case let's call it spool, and again inherit all these allow rules to our SELinux policy. And that's it. This kind of generated SELinux policy you can use with following runtimes, which is Podman, Docker, Buildah, and also Kubernetes. So these are the slides. So let's try it with demo. Okay. So I installed. Can you see it? Good. Perfect. So I install all necessary packages, which is Udica, Podman, and setools. I tell you what is setools in a moment. So let's check what's the SELinux status on this system. Hopefully it's enforcing. Okay, cool. So we have SELinux in enforcing. Let's start the container from the example. So we are mounting /home /var spool and exposing port 21. Okay, container is started, and we see that SELinux label of the container is container_t. So, sorry, it's here, and here are the randomly generated containers. Now you see command sesearch. Basically, I'm querying the allow rules inside the SELinux policy loaded into kernel if there is a present allow rule. The first one is related to /home. /home has SELinux label home_root_t, and if there is no output, which means there is no allow rule. The same situation with the var spool. That's pretty clear. The pod has SELinux labels var_spool_t. There is no allow rule. But on the other hand, for the ports, we can see that container, which is part of these attributes, can basically bind on any TCP ports. Another, let's continue. Now we run Udica, so we need the inspection file of the latest container, put it to standard input of Udica, and the parameter is the name of the new SELinux policy. So let's start it. Policy is created, and Udica recommends to load following templates and final SELinux policy for our container using command se module. So let's do that. And we stop the latest container. Perfect, and we start container again, but with following parameter, which saying to start container with the following SELinux label. And as we can see, it's not running as container_t, but it's our custom SELinux type. And we are running again to sesearch, and as we can see, the allow rules are now there, right? So this container can read and write directories under /home, can access to /var/spool, and again, on the other hand, can bind only on port label ftp_port_t, which is SELinux label for TCP port 21. And basically, that's it. So now you are able to generate a SELinux policy really quickly. So here are the links for Udica, for Podman, if you are interested how it looks like the inheritance in Udica. You can look on Udica POC, and you have the links. So that's it. Thank you. And if you have any questions, I'm ready. Thank you.
thanks for your talk. Now, as a new SELinux expert, I was wondering why this UDITSA part. Could this be in principle also part of Podman? I mean, you're basically already passing all the information to Podman, the port, the read write and read only stuff.
Yes, it's good point. Actually, I discussed it with Podman maintainers to include it there, but somehow, unfortunately, for me, we agreed that UDITSA will be separate too. But we discussed that.
I have a question about labeling. So you said that Podman is relabeling all the files in the container on container start?
Not really. SELinux is not enabled inside the container, right? So the Podman is enabling this stuff on the host level, so which means in the host, right? So there is no SELinux. There is no SELinux inside the container.
There is a lot of file operation.
Yes.
Okay, so if container is like large, has a lot of files, it would be kind of slow, yeah?
Yes, we know about this issue. We discussed it recently inside the SELinux team, and most probably we will work on this for future to to make the relabeling faster.
Thanks.
Maybe there are ways how to do that.
Some other questions? Let's see. There was someone in the back.
Do you have some plan to integrate it into Kubernetes? Because right now you're running Podman, then write UDITSA, and then run Podman again. If I'm writing a Kubernetes or any other orchestration manifest,
yes,
I'm doing it once. So how well it works with Kubernetes, Mesos, and whatever else there is on the market?
Very good question. Thank you for that. In near future, there will be on GitHub. There should be container with UDITSA inside there, and basically you can almost fully automatically generate a SELinux policy inside the Kubernetes. We put annotation, generate a SELinux policy to Docker file, right? So there is an operator. It recognizes that some container was started with that annotation. The SELinux policy is generated. However, there are still technical issues. For example, how to maintain a SELinux policy between the cluster and stuff like that. So it's not easy, but we are working on that. And some proof of concept you can already find on UDITSA webpage.
So maybe a follow-up to the other question. So I mean, it takes a while for UDITSA to generate the policy, but if the policy is really large, is there also a performance hit on every container start due to SELinux having to do that, or is that really fast? Or can you maybe show what the CIL was that UDITSA generated earlier in the thing, just to demonstrate?
I can do that. Actually, this is pretty fast. This is the SELinux policy. What you can see, the first one is that the blog is called my_container. You see that you can see the second and third line saying that inherit all allow rules from these blocks, which is container restricted _net container. The next line is related to capabilities. So this is quite quickly. And all the rest of the allow rules are related only to /var/spool because there is no predefined template. Actually, this is not problem. We can generate a SELinux policy really quickly because UDITSA just parsing the inspection file, which is in JSON format, and looking if there is a predefined block, then just set the list of capabilities from inspection file, and if there is a need, generate also allow rules. But the main issue is related to relabeling. Yeah.
Okay, thank you for your talk. We've got last half a minute, so we will probably end this talk. Thank you, Lukáš, for presentation.
Thank you.